So in our desire to try to control everything, we can do directed aldol reactions. So in a directed aldol reaction, take two materials first. We'll take a ketone or an aldehyde and react it with LDA. So that can deprotonate, and LDA minus 78 degrees C and THF, or some kind of polar aprotic solvent, will make the kinetic enolate, which means that it will deprotonate alpha to the carbonyl on the less substituted side. So this is LDA as base, comes in, takes off that proton. This electron pair moves over to make our enolate. But now, once the enolate is formed, we'll treat it with some kind of an aldehyde to have it react with. And part of why we can do that is that with this big ketone molecule, it would be really hard for it to do an aldol reaction with itself, just because the two big bulky groups would have to get nearby each other, and that's not that likely to happen. We can also affect that by controlling the concentration in solvent. If we have a very dilute concentration of the enolate, then we shouldn't have very many other molecules that we can react it with of itself. So then we can introduce something else to react it with. This electron pair comes back to reform the carbonyl. This electron pair is our nucleophile that goes out and looks for who wants electrons. It's the carbonyl carbon in these cases, pushing this electron pair up onto oxygen. And once again, notice that this is our new piece that we've added. Okay, and check your carbons. There's 1, 2 carbons, 1, 2 carbons that were added. Then from there, once again, we can add water and reprotonate our alkoxide to make an alcohol. And now we've been able to control our reaction so that we're only getting one product, not 4 products from an aldol reaction. Now we can gain even better control of an aldol reaction if we have one of our components of a crossed aldol that has no alpha protons. So benzaldehyde is a classic example of that. If I look at the alpha carbon, there is only one alpha carbon because on the other side is a hydrogen. If I look at that alpha carbon, there are no hydrogens on that spot. We can treat this with a base, and there will be no reaction because we don't have an alpha proton. There's nothing to take off. That can cause this stable enolate to form. So because of that, I can take benzaldehyde and react that with acetaldehyde in LDA, and there's only one possible reaction that can happen, and that is that the LDA will come in, deprotonate my acetaldehyde to form the enolate, which will then react with the benzaldehyde. Now there's ways to control that, to make sure that it's going to react with a benzaldehyde and not with another molecule of acetaldehyde. One is by having an excess of benzaldehyde, and the second is by having the benzaldehyde and the LDA mixed first, which won't react with each other, and then adding the acetaldehyde dropwise, because that way there will be a tiny amount of acetaldehyde, and the chances of that reacting with another acetaldehyde rather than a benzaldehyde would be very small. As all these cases, the electron pair comes back down to reform the carbonyl. This electron pair from the enolate is our nucleophile, comes out and looks for who wants electrons, which is the carbonyl carbon, pushing this electron pair up onto oxygen. And here we have our beta hydroxycarbonyl, except that we have an alkoxide still, so we just need to reprotonate that with water. And you can get your final product. Once again, we only get one product in this type of reaction. We can control it so that we don't get multiple products. Now what happens if I have a molecule that has 2 different ketones in the same molecule, and I treat it with sodium ethoxide? Well, 2 different things can happen if I treat it with sodium ethoxide as far as where can it be deprotonated. So I can deprotonate towards the middle of the molecule, here, to form an enolate. But if I form this enolate, there's not very much that it can do. If this electron pair comes back, there's nowhere particular for this electron pair to go. It can't really attack this carbonyl very well, because if it did that, it would be making a 1, 2, 3-membered ring. 3-membered rings are not very stable. If you remember from before, we've talked about the most stable rings are usually 5 or 6-membered rings. So what would happen if it takes off the other proton instead? So if the ethoxide instead takes off this proton to form the enolate, Now I have this enolate instead, and so now if my electron pair comes back down to reform the carbonyl, this electron pair goes out in search of a carbonyl carbon. Now I would have a 1, 2, 3, 4, 5-membered ring, pushing that electron pair out. And 5-membered rings are highly stable. Okay, so let's number this. 1, 2, 3, 4, 5, and try to make sure we place our things properly around the ring. So at the 2 position, I've got a carbonyl. This electron pair came back to form a carbonyl. So at 2, I have a carbonyl oxygen. 3, 4, 5. At the 5 position, I have an O-. Also at the 5 position, I have another methyl group that's coming off there. So that's my intermediate that needs to get reprotonated with water. To form a product. And again, you should be able to go back and count your carbon. I have 1, 2, 3, 4, 5, 6 carbons in my starting material. It just cyclized, so in here I have 1, 2, 3, 4, 5, 6 carbons. And you'll notice also that once again, this is a beta hydroxy carbonyl, or an aldol product. So this can actually be a very useful reaction for making 5- and 6-membered rings.